unusual for this class, but it won't be for long. So we're going to talk today about concrete. I know you'll find that surprising, the class about concrete and masonry. Before we do that, we should probably cover over a little bit of housekeeping. I'm sure you've all seen the announcement from the Chancellor that we are going to not return after the Thanksgiving break. And we're going to take this class and any other classes that are online offline. And we're going to do them remotely. How many of you are going to be in Menominee during that time? Okay, so if we decide to do a couple of things and maybe get together, we could take some videos. But for the most part, we're going to go to online. This is not an ideal class to teach online. As you know, we spend a lot of time in the lab. And then if I was to just film myself in the lab, I'd have to lift heavy things. That's not going to happen. Right, heaviest thing I get to lift all day is a pen. So what we're going to do is we're going to go back to a more traditional style of learning, and we'll get some videos thrown in of doing various tests. I don't want anybody to worry. We've had some assignments turned in. Not all of them have been graded, but everything is looking pretty good, and everyone is going to do very well. So recording. So the online classes will cover over some of the things that we're doing. How many of you will not be here on Monday? Good. On Monday, we're going to walk through the building. We're going to learn how to read masonry walls, something that's not very easy to do when we're on remote control. So we'll have to catch up a little bit on Monday and take a slight detour. But where we are so far, well, we made our mixtures the other week, and we have concrete mixtures, and we can, given the right tables, and you can look up, you can design a concrete mixture. If I tell you the properties of your cement and aggregates and the design properties that I want, you could go on from there and calculate what you need to do for mixture proportions. Then we go into the lab and trial batch it. And this takes us to about 1975. A little bit the things we have to catch up to get to 75. One of them is air and training. Well, we talked about putting air in concrete, right? What do we put air in concrete for? Well, by the end of the day, you will know. We put it in for durability. And it developed in the 30s. We get some small bubbles. And those small bubbles are distributed throughout the matrix. They're very small. In the spacing between them is in the order of 0.008 inches. Very small bubbles, very close together. And that gives the water somewhere to expand to. We've known how to do that since the 30s and reliably since the end of the Second World War. That's why you can place concrete outside and never worry about it, something you couldn't do 60 or you couldn't do 100 years ago. But we get some limitations of our physical systems, one of which is our Portland cement at a water cement ratio of about 0.37, we have a problem, right? Can't get it to mix. And we showed you that. And then we used an admixture. So an admixture, very simple functional definition, something that is not cement or aggregates or water that's added to the concrete. And so we have two kinds of admixtures. We have chemical admixtures that are generally liquids, but could be powders, and mineral admixtures that are almost always powders. Not powders, powders. So we have chemical admixtures, and we have what we call mineral admixtures. And today we're going to talk about what those are, what you need to know about them from a mixed design and a concrete performance point of view, and why you generally shouldn't be able to find concrete without a mineral and a chemical admixture in them except in a museum. Because we can make concretes that would otherwise have been impossible. So let's start with our mineral admixtures. Remember we talked about Roman concrete? And we said that we used pozzolans. And pozzolans were the finely divided materials that are emitted during a volcanic eruption and that were collected by our friends the Romans after they buried all those people. And you mix them with lime and water. Lo and behold, you got a hydraulic cement. You got something that sets. Well, we have some examples of modern volcanoes that we control, that we use to do work. The first is, if we burn coal to get heat, and we get ash as well. There's a little smokestack. Here's our coal burning facility, which we're using to generate steam to turn a turbine to have electricity so that we can not go to sleep at 5 o'clock at night. It's fairly dark out there right now, right? So we need electricity for that. And when we burn the coal, we get heat. We get some ash that goes to the bottom of the burner. Keeping in mind how creative we engineers are, that's bottom ash. And then we have some molten particles that go out the smokestack. They go flying out the smokestack, so we call that fly ash. And fly ash are spheres, and they're glasses. In other words, they're amorphous. They're not crystalline. And they're almost entirely silica and alumina. Now, if you remember from our chemistry of cement, silica and alumina is what we have in the cement. If we take that silica and alumina and we put it in the presence of calcium hydroxide, which we get from cement hydration, we make calcium silicate hydrate glue. And the cool thing is that this glue is indistinguishable from the one that we made from the Portland cement in the beginning. Do you remember we took a sample, we set it out in water, and we had some white growths on the outside? We drove the calcium hydroxide out. If you put in enough pozzolan, in this case enough fly ash, you won't have that white material because it's been reacted to form more glue. Why would we want to do that? It's the same reason that we always want to do everything. Why fly ash? Because the cost goes down, the workability goes up. We need less water for a given slump. If we need less water for a given slump, what else does that mean? Our water to cement ratio goes down, and therefore our strength goes up. So, pretty neat material. And because it's made of, it looks under the microscope like little spheres, it becomes quite, those spheres don't, they pack nicely and they don't cover, they don't require as much water to cover them as a crushed particle like cement. So if you use 15 or 20 or 25% fly ash, you start to have mixtures that are more workable. There's a downside. If you put the fly ash into the concrete mixture, it can't react until the cement has. So it delays the set. It slows down setting, which might be a problem. And how much it delays set has a great impact. If it delays it by 20 or 30 minutes, how can you tell? If it delays it by 10 hours, everybody knows. So somewhere in there you need to know that, and what happens now is your cement fly ash compatibility is important. Okay, so that's important. And it's generally true. Fly ash is not manufactured, right? It's a waste. It's generated when we burn coal. And so for a while we had tons of it everywhere. There's a big problem now. We don't burn as much coal. And when we don't burn as much coal, we don't generate as much fly ash. And a lot of problems that we solved in concrete mixtures with fly ash are coming back to say, you thought I was solved, but looks like you ran out of fly ash. So, specific gravity is 2.68. It's governed by ASTM C618, and there is a type F and a type C, and this is low calcium and high calcium ash. Type C fly ashes are typically hydraulic cements in their own right, but we don't use them as hydraulic cements very often, so we can not worry about that. So we have a source of glassy material that is relatively inexpensive, and we can put into our concrete and get us more glue. If it comes from our modern volcano. What other modern volcano do we use? If we go down to Chicago, what do they make? Lots of heat and fire. Steel, right? So steel is manufactured in a furnace where we're blasting in oxygen. We're blasting in air, but we only care about the oxygen. Sitting on the top of our iron ore material and some limestone, down here we have iron, molten iron. And up here we have the non-iron components that came in with our iron ore, and this is called slag. If we take the slag and spray it into water, then we trap it as a glass made of silica and alumina. It's to be about the size of sand. Then we grind it, and we get a powder that is a pozzolan, just like fly ash. Now it has some problems. Because it's ground, it's not spheres. So adding slag may or may not help you with your water reduction. But it definitely will act as a pozzolan. It will take calcium hydroxide and water, combine with them, give us more glue. Hooray, right? And we use a fair bit of slag. It's a very interesting material because it's latently hydraulic. At room temperature, it'll react just with the water, but it takes a lot of time. At 140 degrees, it's taken off like a rocket and reacting all by itself. So it has latent hydraulic capacity. So if you do something that gets the concrete hot, up in the 100-degree range, then the slag starts to behave as a hydraulic cement. So it's kind of both. It has latent hydraulic tendencies. It's activated by heat and by sodium and potassium and calcium for that matter, which are the alkali metals. We refer to them generically as alkali. So it's alkali activated, it's heat activated. And there's a lot of people, as we continue to deal with the sustainability aspects of concrete construction, that are now taking slag, blending it with an alkali, and it's a hydraulic cement all by itself. Don't spill any on yourself because the alkali will burn through your body. But you know, it's a fairly exciting material. This material conforms to ASTM C989, and it comes in 3 defined flavors: grade 80, grade 100, and grade 120. And this grade refers to the percentage of the strength you would have at 28 days as compared with a concrete with the same amount of material, but just cement, not slag. Grade 80, strength's going to be 80% at least. Grade 100, it'll be the same. 120, it'll be higher. And of course, we control that by grinding it finer. In general, this is an increasing fineness of the grind. Finer the grind, the smaller the particles, right? And so slag we see all over the place. And in fact, I brought in last week 2 40-pound pails of slag so we could make some slag containing concretes. You know, best laid plans of mice and men, right? So slag looks like cement. So does fly ash. Fly ash is kind of brown. Slag is kind of white. But it has a really interesting behavior. Slag, when it's mixed with Portland cement and it's cured where there's not a lot of oxygen, like under a curing blanket. Remember we covered our samples with blankets? Under a curing blanket or under water, it turns green-blue from the sulfides, the sulfur compounds that are present. And if you take that green concrete and you put it out in the air with oxygen, it'll go to a much lighter color. But if you're not careful, you can run into trouble where someone calls and says, "Oh my God, my concrete's blue." You say, "Well, it's because there's probably slag in it." No, they said there wasn't any. Well, we better come down because there is. Okay, famous story. A lot of granular blast furnace slag made in Canada. They also on the lake in Hamilton have a lot of steel plants, and so as a result, when they built the Canadian Embassy in Washington, they said, let's make it really brilliant white. Best way to do that is lots and lots of slag. So they stripped off the forms, and then they sealed the concrete surface, which prevented oxygen from getting at the surface. So for about 3 years, it was kind of this mottled blue, green, white catastrophe. In fact, the company that I was working for in Canada at the time got a call and said, what can we do? And we said, well, just get some hydrogen peroxide, right? Lots of source of oxygen, scrub it into the surface. And they kind of didn't think that was really very relevant, didn't want to try it. So they talked to a couple of other people who had other ideas, and then of course they came back, put hydrogen peroxide on it, and it turned white. So there you go. We also, and we're all victims in the cause of this, we use a lot of silicon metal now. Where do we use silicon metal? Don't all talk at once. You all, I guarantee, have used it today, and some of you are using it right now. See, you're using it right now. Did you know that? Oh, yeah. What are the chips in your electronic device made of? Silicon. Silicon, right? Silicon Valley. Silicon metal is Si. You take silica, you heat it, and you make, under reducing conditions, right, losing electrons, you make silicon metal. Just like you make iron. Well, we do that in a furnace. You'll notice all of my pictures all look the same. And there's a smokestack. And we're taking our silica sand, we're converting it into silica, we're reducing, so we're probably making hydroxyl in the solution. And coming up this smokestack is small trace silica. So small that the particles in the smoke are smaller than the particles in cigarette smoke. That for every, if you're at 5% in concrete, every cement grain has about 10,000 silica particles. Now these are collected up the smokestack, so what shape are they going to be? Just like the particles of fly ash, right? They're collected, they're liquid, and they're cooling, and they cool as a solid, but they're a droplet when they were liquid, so they're a sphere. But now we have a big problem. Because silica fume, the particles are so fine that if you took silica fume in a jar and you poured it out here, it would kind of hang in the air because it's a smoke. Silica fume, the silica smoke, is what we call it. It's there's lots of it made whenever you make computer chips or ferrosilicon steel, which is a very particular type of corrosion-resistant steel. Silica fume is also a pozzolan, but every one of these particles has a surface that needs to be coated. And so once you get at about 5%, the cement particles aren't in charge anymore. Now it's a silica fume. Now remember we showed you the aggregate where it's just full and we could pour sand and we could pour water in still. That same thing happens at the cement scale. The silica fume really densifies that concrete. Amazingly densification. However, at about 5%, it starts to get so full of tiny little particles that the water demand goes through the roof, and it gets very sticky and hard to trowel. And just like a clay outside, right, with very, very fine particles, you can start to develop cracking before it sets. Plastic cracking, plastic shrinkage. When they first came out with silica fume, when we first started using silica fume in transportation structures, we were using 12 and 15%, probably because we hated the finisher. And in the lab, you got great, fantastic concrete. Very dense, water won't go through it, lots of good things. Except it cracked every 6 inches in each direction. So in between the cracks, it was really dense, but it didn't matter because the cracks were too tight together. So we used 4, 5, 6%, 3%. We want to improve the properties of our concrete. This pozzolan, because it's so finely divided, will increase the compressive strength by densification starting at day 1. So with ordinary Portland cement, we can get concrete blended together. We can make 7,000 psi concrete without too much additional work. After that, we add fly ash and or slag. We can get up into the 12,000 psi range. With silica fume, I think the record now is in the 25,000 PSI range, which of course, 25,000 PSI compressive strength, that's beginning to approach the yield strength of steel. Very, very dense concretes, and all made with these other materials. Now, obviously, I need low water to cement ratios to do this. And I need to understand that the pozzolan is going to change my strength. So just like I had an OPC, ordinary Poland cement, water cement ratio versus strength curve, I could get one for a fly ash and cement curve or combination, a slag and cement combination, a silica fume and cement combination. Or I can have ternary blends, some fly ash, some slag, and some cement. And the St. Croix Bridge recently completed. By the way, the project manager on the St. Croix Bridge, where did he go to school? UW Stout. They had transfer beams at the top of each of the piers that consisted of a quaternary blend: cement, fly ash, slag, and silica fume. Carefully proportioned to give us concrete that the state said they didn't think could be made. So that'll teach them. And that's what I was hoping to do. I've got a bunch of cylinders that are many, many years old because I developed those mixtures for St. Croix, and they'll break at 20,000 PSI at 56 days. You pick them up, they don't look like concrete. They look like a piece of rock. They look like a ceramic. They're so shiny and they're so heavy. But we can make wonderful things. But here's the cool part. We didn't do it for strength. We did it for durability. We'll talk about that next. Now we've got all these wonderful materials, and so if we look at those three, we have fly ash. Which conforms to ASTM C618, slag, which is ASTM C989, and silica fume, which is C1240, I think. Some people, you'll hear the term microsilica, same thing. Okay, and the particles are so tough to move around that we densify it. We press it together so that it can be moved. Otherwise, it just sits there. You put 50 pounds in a silo and the silo is full, and you're not putting any more in. To be careful, people wear masks around it. If we look, what does it do to setting? What does it do to strength gain? Early and late. And what does it do to durability? Well, fly ash is going to increase the time of setting. It's going to be slower. Early age, it's going to reduce the strength. Later age, it will increase it. Slag, it's going to be neutral for setting. It's going to be neutral in early age strength, should increase the late age strength. Silica fume is going to significantly decrease the setting time. It may decrete very fast. Strength gain early and late. Durability improves with all three. So we need to define what durability is, but we have to talk about chemical admixtures first. But this is the real driving force for using these materials, is we can make more durable concretes. Sometimes, the G-Wiz 25,000 PSI, on one Wacker Drive in Chicago they used 18,000 PSI in design. I did one last summer in Sioux Falls, right? The buzzing technological high point of Sioux Falls. They needed 12,000 PSI concrete for an apartment building. So I ended up working for the ready-mix producer, and they said, can you make 12,000 PSI concrete? Because we've never made anything higher than 6. I said, that's no problem. We don't need silica fume. We can do it with slag. So we did. But in order to get some of these things to work, in particular, what these same three guys do to slump. Fly ash increases it, slag has no effect, silica fume kills it. What we need to do is go to our chemical admixtures. And we already talked about one, so we'll visit him very, very briefly. Air and training agent is a fancy soap. Okay? In fact, if you're in a pinch, Dove dishwashing detergent is an excellent air and training agent. Okay? And they make bubbles. Some, like Palmolive is not, but Dove is a good one. These need to conform to ASTM, I think it's C289, and that's old. They started at C1, right? So C33 for aggregate is really old, and when we talk about general Pozzolans or other Pozzolans at C1790, that's about where we are. So 289 is not too bad, not old, not new. It consists of a soap that's stable at high pH with a high solids content in the water. And so you will see when we talk about durability, we specify the air content, but what we really mean is we want to know the air structure. So that was our first one. Had our own admixture, had its own specification. But we have a bunch of them. ASTM C494 is chemical admixtures. And we'll talk about some of the things that we're doing that are a little bit, that are common to see. We have a type A. Type A admixture is a water reducer. What does a water reducer do? It gives you the same slump at a lower water content. So it increases the slump at fixed water. Or it decreases the water at fixed slump. And so the way we would handle this in our mix design is we'd say our water reduction is minus 10%. So if we were to say, I look up at our table and we need 280 pounds of water, well, if we're going to use a water reducer, a type A, we would only use 280 minus 10% of 280, which is 252 pounds. So we reduce the water. But what we really do is we increase the strength. At a fixed water to cement ratio, the strength will go up because we have water reduction. So that is always if they had called it a cement reducer, they never would have seen the light of day. The Portland Cement Association would have killed them. Type B is a water reducer that retards. What does retards mean? It means it slows down the set. So if you need an extended amount of working time, it will slow down your setting so that you have that extended working time. Say if it's really hot outside and the concrete is being made hot, we may in fact want at that point to say we're going to use a retarding water reducer, or just a retarder for that matter, in order to make sure that we are going to get our performance. A type F admixture. That's the one we saw in action, a high range, water reducer, which may have 15 to 20% water reduction, handled the same way as the type A. And a type G is high range, water reducer, retarding. They're the most common that you would see. And the reason that we say we shouldn't have concrete except in a museum that doesn't have these materials is because water reduction means we can use less cement. Pozzolans, most of which are waste, you'll notice are garbage from someone else's projects. Although silica fume is the only material we ever kept track of per pound, we would put those materials in because we're going to get more out of our cement. The admixture lets us get more out of our cement. There's other admixtures. There's a type S admixture which doesn't have any effect. That means it doesn't deteriorate the properties of the concrete. It typically, a good type S admixture might be one that holds the concrete together, makes it less prone to segregation when it's flowing concrete. Types D and E, I can never remember. Oh yeah, okay. A type E admixture is a water reducer that accelerates. What does acceleration mean? It compresses the time. Let's say it's cold outside. We want the concrete to set before it freezes. So we're going to want to accelerate it. Okay. So we have ASTM C494 type F, or sorry, type E. This is water reducing and accelerating. So a retarder. Anybody work on cars? You know, you have an engine retarder, slows the engine down, and your accelerator speeds it up, right? Same thing. Has the same meaning, not by the same methods, but the same meaning. We can use all sorts of cool things to do all sorts of strange things sometimes. We can use pumping aids. We can put in admixtures that will suppress the formation of freezing water. We can put in admixtures that are going to change the color of the concrete. We can put in admixtures that will stop it from hydrating until we put the antidote in, and then it'll start. We can do all sorts of things and manipulate that chemical reaction or manipulate the physical properties. Do you know what a water reducer does? How it works? It socially distances all the cement. It puts a repelling force on all of them, the negative charge, so they can't go together. I've never been able to tell anybody that it's social distancing of the aggregate, of the particles, but so it is. Okay? They act to push things away. You have to be careful about something called admixture compatibility. Because if you put in a retarder and a type S stabilizer and a type S VMA and what else do I want in there? An air training agent and a pozzolan, maybe two pozzolans, and a cement, it is possible to randomly find a formula that nobody else, because they don't check all these things, right? You're the manufacturer. Put them together and the concrete won't set. Or worse, it'll set so fast you can't do anything about it. So admixture compatibility is a big deal. We handle these admixtures, we handle these pozzolans because we have problems with concrete performance, with durability. So we know that the structure that we make, these are concrete to manufacture, has to be strong. But it also has to be able to withstand the loads that are placed on it in the environment. We have a very severe environment from a concrete point of view in Wisconsin. We freeze the concrete routinely, and we throw de-icing salts on it. And even if we don't mean to, if you walk out there after the university puts a bunch of salt down and you walk across the sidewalk, you're tracking salt even if we don't put the salt on the sidewalk. One of the silly things that Semstone used to do is tell people, don't put salt on your concrete the first year. Not a bad idea, because if it's marginal concrete, it might be damaged that wouldn't otherwise be damaged. If it's bad concrete, it's not going to fix it. But then I pointed out to our risk management committee that means we're telling people, use our concrete, but don't put salt on it. Then when some old lady walks, because the Archdiocese in St. Paul in the cathedral was told that, can you imagine some old lady slipping and falling, and her son, the lawyer, suing us, saying, you said you couldn't put salt on it. So we don't, well, I think they still do say that, but I have a clear conscience. We need to worry about freeze-thaw durability. And this is distinct and different from frozen concrete in the plastic state. This is hardened concrete that's exposed to freezing when saturated. And if we don't have any voids, if we have no bubbles, then this open space in the concrete that's full of water behaves like a hose would if you froze it. It splits open, right? You may not tear the concrete apart on the first cycle, but you do a little bit of damage, you do a little bit of cumulative, eventually the concrete goes away. You see lots of it, and the gutter down in front of where you can park just out here is atrocious. These depth freezing and thawing is well described. We tell people in our code that you have to use an approved air and training admixture that conforms to the SDM standard, and you need an air content for 3/4 inch concrete if your air is somewhere between 5.5% and 8.5%, that you should be okay. And this is the total air content. And it's a really easy, it's a good spec, because I can bring out an air meter, fill the meter up, check it. It's a complicated piece of equipment. Balances a known and unknown volume of air. Uses Boyle's law. P1 V1 is P2 V2, and the only thing we don't know is V2. And away we go, and we can measure it. What we really care about is how close together the bubbles are. So if it's 6 to 8, or 5.5 to 8%. Like at 5.5 to 8.5%, you're going to be great. Everything will be fine, nothing to worry about, as long as you use the right air and training aid or admixture. But it could be that you're down at 4% and you're still okay, because if the bubbles are really small, then they're really close together. And that's where you need to do an analysis. And that's why you want to check concrete for air. Now, why do we have an upper limit? The lower limit is to make sure that the bubbles are close enough together, right? The upper limit is because for every 5%, for a 1% increase in the air, the strength goes down 5%. So if you remember, we have two lines on our curve, right? One for air-entrained and one for non-air-entrained concrete. And for a given strength, we need a lower water to cement ratio for air-entrained concrete in order to get the same strength. And that's because what's the strength of the air bubbles? Not particularly high. So we have this air problem that we have to deal with. I'm trying to cram about 3 lectures in. That's why we're going so fast. So that's why we're recording it. So we have these air bubbles. They're close enough together. Our upper limit is set because we worry about strength. But that's not enough. That's what mathematicians call a necessary but not a sufficient condition. Air-entrained concrete will not be damaged by freezing and thawing so long as the air entrainment is adequate the water to cement ratio was low, which restricts the amount of freezable water, and the concrete has had a period of drying out after being adequately cured. So we need air, we need a low water to cement ratio, 0.45. If there's no chlorides, no salt, and 0.40 in the presence of chloride. Air 5.5 to 8.5, 5 to 8, 6.5 to, or sorry, 6 to 8. Everybody, MnDOT, WSDOT, the building code, city menominee, everybody has their own numbers. And that it's allowed to dry because it has to be cured, right? So that we make the pores really small and then we get the air out of them. Because if you have the pipe and it isn't full of water, then the water can freeze, no problem. It has to be full to give us a problem. And there are spaces in the concrete that once we let it dry once, we can never get water back into it. They're that small. And those are the ones we want to empty. And this approach is taken regularly. And so if you see concrete that is damaged by freezing and thawing, then someone has made a mistake. Either the designer, possibly, the contractor, maybe, the ready-mix producer, maybe, or the finisher, almost for sure. Because if you take a steel trowel and you wipe back and forth and densify that surface, what am I squeezing out? All my damn air bubbles, bastards. I spent over a nickel putting those air bubbles in, and now you're taking them out with your precious trowel. So you need to make sure that all concrete that's going to be flat work like this stuff was out here is not steel troweled. If you steel trowel air and drain concrete, it will cause many problems. One, it'll pull the air out. Two, you may form a film of little air bubbles that are compressed and elongated down about 3 millimeters, and then the surface just peels off. Also a bad day, right? Because it generally happens as someone is starting to put in the cabinets in the floor and they go like, hey, how come the floor falls apart? So this last spring, I spent quite a bit of time looking at a project in the south or in the northwest that you could pick up sheets of the concrete surface if you were careful about the size of this piece of paper, size of a dinner plate, and just lift them off. You can imagine how well that is in an area that's supposed to be traveled by 10 or 20,000 people walking on a daily basis, right? It's going to be gone. So to repair it in a hurry. The advice is don't do it. And then the contractor was someone you would all recognize, a big contractor. So it happens to everybody. Don't let it happen to you. What else do we have in terms of durability? How about abrasion? We can wear our concrete away, right? If we scrape things across it all the time or we run rubber tires across it, we're going to continuously abrade that concrete. So surface abrasion is controlled with the water to cement ratio. The lower the water to cement ratio, the higher your durability. We can have exposure to de-icing salts or seawater. Okay? We decrease our water to cement ratio, increase our durability. We have chlorides. Have any of you taken statics yet? I think some of you have, but you're not here. The two guys who have taken it are not here. So, if chlorides, the chloride part of sodium chloride, de-icing salt, as it penetrates through the concrete, comes down to the steel, causes it to rust. The rust has a density of about 1/10 or of that of the iron. So for 1 pound of iron or 1 cubic foot of iron, You get 10 cubic feet of rust. That's happening inside the hardened concrete, breaks the samples open. So we care about the permeability or chloride ion penetration of concrete. They cause corrosion reinforcing steel. And when I was a little bit older than you are today, I started studying at a very serious level. Actually, no, when I was, maybe a year older, corrosion reinforcing steel and concrete. It's my specialty. And at the time, someone said, why are you bothering to do that, man? Haven't you been out on a construction site on a bridge? What do we do? How do we provide corrosion protection? I just wanted to let you know that steel's heavy, right? How do we provide corrosion protection? I didn't think I was quite that high off the ground. What do we do? What's the green stuff? We coat it with epoxy, right? It appears that the epoxy lasts about as long as it takes for the chlorides to get down there. This is my favorite bar. This is the number 10 non-weldable 60 KSI bar from Gyardo in Missouri, but it's really much more useful. Sometimes I carry around that yardstick. This one's a lot more useful in convincing the students of my correctness. Sorry about that.
Pretty good.
All right. The epoxy coating doesn't work. Several places have said, just forget the epoxy coating. We'll deal with black bars. Several of them have gone further and said that we are going to use stainless steel and lots of other things. In order to do this, we increase our pozzolan content, particularly silica fume, but also slag, and we decrease our water to cement ratio. You should see there's somebody showing up every time we talk about one of these, isn't there? What's showing up each time? Water to cement ratio. Sulfate. There are naturally occurring sulfates in the soil. Also, there's sulfates in sanitary sewage. Sanitary sewage, yes? You going to say something? So sanitary sewage runs in concrete pipes down to a concrete treatment plant where it gets treated. Those sulfates all come in. If you go across the border of Minnesota into the Dakotas, the sulfate soil, the content of sulfates in the soil increases, and that's a problem because sulfate plus the glue goes to calcium sulfate hydrates. This expands. So sulfate soil will cause deterioration of the concrete. How do we change this? We increase our pozzolan content. We change our cement chemistry, and what do you think? We decrease our water to cement ratio. So you're learning. If I want to keep water out, I decrease my water to cement ratio. One very nasty problem are aggregate reactions. In particular, the alkali aggregate reaction. We have silica that's amorphous in the aggregate. That combines with the alkalis from the cement, and we get a gel. Anybody ever buy a briefcase or a wallet or a leather coat, and you dig around and there's a little packet there and it says silica gel, do not eat? They don't eat it. You know. What's it there for? Keeps moisture out, right? Silica gels will suck up all the water in the room and hold it inside them, and they'll swell a little bit while they do that. Perfect, right? Keep your briefcase nice and clean. Unfortunately, if you start to develop and react and form a silica gel inside your concrete, That's not so perfect, because it keeps pulling water in from the environment, swelling, cracking, making it easier for water to get in, which makes it swell more, which makes it crack more, which makes it easier for the water to get in. You get the picture. The concrete will expand and come apart. How do we prevent ASR? Well, Pozzolans are quite useful. We'll increase those. And then we don't want the water to get in, so we're going to decrease the water to cement ratio. And the reason we decrease the water cement ratio each time is because as the water cement ratio goes down, the space available inside the concrete that is not a solid goes down. That's why the strength goes up as the water cement ratio goes down. Abrams had no idea. We know this from other porous materials we developed mainly for the space program when we were sending people to the moon, which hopefully we'll do again. Only because they're going to have to build the moon base out of something, and that's not going to be steel, right? What do you build the moon base out of?